So I'll start the recording now. So, what is going on with this? Believe it or not, if we had to go through and rank these according to... never mind, let's not do it that way. Both A and D are pretty darn close to the exact same answer. D is technically the correct answer. A is the not quite there answer. So what happens when we go through and react? Well, the first thing that happens is we go through and we form our borane intermediate. So the borane reacts with a pi bond and it adds the boron and the hydrogen across the double bond. Okay, so our very first, well, I'm just going to erase everything up there. So our very first product from that very first step is we would have the hydrogen and boron added on there. So we got two spots. And I'm going to label these A and B. One of those is hydrogen, one of those is boron. Which gets which? The hydrogen should be at which position? Or the boron should be at which position? A for boron. Okay. Which would suggest we put the hydrogen at B. Take a look at your answer. Final answer, D. Where does it look like the hydrogen went?
A.
It looks like the hydrogen went to position A, actually, not to position B. Because if we go through and look, that carbon was our formal triple bond. That carbon has two hydrogens on it. No boron reagent or anything like that. This goes back to the reactivity of our borane structure. When we look at boron and we draw out its Lewis structure, we have BH3, right? What is the hybridization of BH3? sp2, which means what is left over on that boron? An unhybridized p orbital. What can we put into that unhybridized p orbital? Electrons. Where are the electrons coming from? The pi bond. Which carbon holds the larger negative charge? A or B? B. Draw out your resonance structures. If we split our charge, B is going to hold the negative charge better than the A carbon. Okay? And that has to do with, again, our electron repulsions, all sorts of other fun things along those lines. Which means when we coordinate the hydrogen and the boron to this structure, the boron goes to position B and the hydrogen goes to position A. Look at that, there's an H. Let's fix that. Right? And officially we'd string out with our other hydrogens. This ends up being our first-ish intermediate.
Wouldn't the boron have a third hydrogen, or is that just...
It does not have that third hydrogen. Where did that third hydrogen go?
To A, or is that...
To the A carbon. That's where that third hydrogen went. So remember, what we're forming is a pseudo-tetrahedral, or not tetrahedral, pseudo-four-membered ring. That four-membered ring is happening there.
So the THF
That's our transition state.
It's just
What is the role of the THF?
solvent,
Solely the solvent. That is the only reason THF is being put in there. Okay? We now have this structure. Okay? That is the end result of the first step. We then add the peroxide. What the peroxide will go through and do in a pseudo-similar four-membered ring, at least in my twisted world, the result is we cleave the boron and we end up with, whoops, double whoops, hide that again. With our OH on the outside. The reagent adds hydrogen and OH to an alkene just like it would to an alkyne the exact same way it would add to an alkene. There is no difference in that reagent. Okay? So that might be where you stop, and theoretically that is where you should be stopping, okay? Or where I would have hoped you would have gotten to. I added this as an extra wrinkle because that structure is inherently unstable. Questions about what's shown up there so far?
Why is it unstable?
The exact why we'll get into a little bit more when we talk about the carbonyl functional group later on in the semester. If you think back to earlier in first semester, we actually addressed this exact structure. We talked about it. This is an interesting functional group because we have right here, what? An alcohol. And we have right here an alkene. Because we've now put these two functional groups on top of each other, we have invented a new functional group. That child of a functional group is known as the enol. Okay. The enol tautomerizes through a sequence of hydrogen transfers to become the carbonyl. Okay. In a very crude mechanism. Oh shoot, I'll just redraw all that. The electrons come down, we form the carbonyl, the pi electrons come out, pick up H+, and we have our carbonyl. Okay. The carbonyl is in equilibrium with the enol. The carbonyl is inherently more stable. The exact dynamics of that were briefly addressed in first semester. Beyond knowing that it needs to happen, you don't need to know the mathematics behind all of it. But you can look at bond energies and all that other fun stuff to prove that the carbonyl is more stable than the enol. Okay. Questions on that? The textbook provides a much better mechanism, or more accurate mechanism for this whole process. While it is more accurate, it is also equally more confusing. So what I've shown you in that video and partially through this one is a much simplified mechanism that gets you to the same result. The hydrogen and the OH are added to the same side of the pi bond. Okay. If we're starting with an alkyne, that tautomerizes. So we'll keep hearing that word, so I might as well write it out. And the variations of it, tautomers, tautomerization, all that fun stuff. Okay. We'll tautomerize over to the carbonyl. Okay? Exact same thing. If you remember, we have another reagent that allows to add hydrogen and OH. What is that other reagent? There's a couple different options, actually. Begins with an M or an H, depending on your opinion. Mercury. Your mercury acetate, followed by sodium borohydride, adds hydrogen and oxygen, or an alcohol, across a double bond. If we make that double bond a triple bond, we get the exact same result. We form the carbonyl. What's the difference? If we started with this exact same compound, yeah, I'm just going to have to do all this. What would our product be if we had instead used the mercury? Well, we said it adds hydrogen and OH across a double bond. Where does it place the hydrogen? Where does it place the OH? You change the positions. The mercury acetate adds your hydrogen and OH in a Markovnikov type fashion, and what we would end up with would be something like this. What functional group do we have? An enol. What does the enol do? Tautomerizes to become the ketone. Okay? So watch out, your alkynes can get tossed in there and mess with your head a little bit. We'll see them pop up again when we go through and do our oxidation reactions. Okay. Other questions? Okay. What we're now going to move into, I don't know why I wrote 19.5. I think that's a typo from a previous thing. This is really looking at chapter 24. And in chapter 24, we have a couple things going on. The bulk of chapter 24 is the Diels-Alder reaction. Okay. There are now 2 lecture videos on the Diels-Alder reaction posted and available through YouTube, Canvas, all that fun stuff, both from the lecture and lab side. The first video is the, holy crap, look at all this stuff going on within the Diels-Alder reaction. How does it work? I'm not telling you. Second video, I tell you. Okay. Go through all the details and show exactly how that works and comes together and all of the variety of results that come out of it. Be aware, okay, the Diels-Alder reaction is an inherently 3-dimensional reaction. Everything we really deal with throughout the semester, we can get away with drawing on paper because the reactions we can roughly equate to being 2-dimensional, sort of. The Diels-Alder reaction is 3-dimensional through and through. There is no easy way to draw it in 2 dimensions on your paper, which means there's no easy way to just look at paper and say, oh, I get the answer, short of just having seen the answer and memorized what the possible answers are. I highly, highly, highly encourage model kits. In fact, I may even bring out model kits during lab to force you to play with them during the lab situation. Okay? If you have any problem seeing the Diels-Alder reaction, you need to talk to me so we can get that figured out and get you spatially aware of what's going on within it. Okay. After that, they've got this weird, like, 2 sections worth of these oxidation reduction reactions, and in particular, just the oxidation. So it's important to review what reduction and oxidation mean. In Gen Chem, we had loss of electrons, gain of electrons. Yay, we've memorized that. That worked well. We've got now organic. What happened in this reaction? There's at least 2 correct answers. 3 correct answers. We added hydrogens across the double bonds. Yes. So we could even say this is an addition reaction. Right? But that doesn't mention anything about this whole redox thing that I'm mentioning. What type of reaction is this? It is a reduction and oxidation reaction. It is a redox reaction. What did you actually call it?
It's a reduction.
You just said reduction. Okay? In Gen Chem, when we talk about reduction and oxidation, we always said redox. Why?
Because you do both.
You have to do both. Okay? In organic, you'll hear us refer to them as reduction reactions and oxidation reactions. You won't see them strung together as redox. Why?
Because you're just referring to the organic.
We're only looking at the organic compound in our reactions for organic chemistry. So what we have to do is look at just the organic compound, that cyclopentadiene, and it turned into cyclopentane. All we did was added hydrogens across that bond. So what happened to the cyclopentadiene? Did it gain electrons or did it lose electrons? Do you see any electrons? It's not super obvious. So it might be nice if we had an easier way to look at an individual reaction and decide, was it reduction or oxidation? Our organic tweak, reduction, increase in hydrogen bonds or a decrease in oxygen. An oxidation reduction or an oxidation reaction is an increase in oxygen or a decrease in hydrogen. Sometimes they happen together, sometimes they don't. Right? So if we go back and look at our carbon structure, what's happening to it as it goes from reacting to product? Very hard to see the electron transfer. Electrons are actually transferred in the course of this reaction. Okay? But if we change to our organic definition, what did we say happened? we increase the number of hydrogen bonds to our carbon structure. That reaction is referred to as a reduction reaction. Okay? So being able to look at a reaction and kind of quickly decide, is it oxidation, is it reduction, is going to be an important skill because that can narrow down some of the reagents. Okay? The other option, which I'm not even going to open too much of a can of worms on this, is we can classify oxidation states. Once you know the oxidation state for every atom, you can then say how did it change through the course of a reaction. To determine the oxidation states, again, very briefly mentioned in first semester, you can look at the electrons around an individual atom and cleave all of the bonds homolytically, total the electrons around the atom, minus the number of electrons around the atom according to heterolytic cleavage. What does that mean? Real quick example with the first one. Okay, what is the oxidation state of the carbon? Well, we go homolytic. Homolytic means the electrons in the bond go back to their parent atoms. So how many electrons would be around the carbon? 4. Minus the heterolytic cleavage. Heterolytic, the electrons go to the more electronegative atom. Which one's more electronegative, carbon or hydrogen? Carbon is more electronegative, slightly, but it is, which gets us a -4 oxidation state. Okay. If we go all the way to the extreme, you should notice that that one's a +4. What happens as I go from CO2 to methane? What happens to the oxidation number? It's another word for decrease. It was reduced. What happens as we go from CO2 to CH4? We added hydrogens, there's our reduction. Okay, you could also look at the reverse. So we go from -4 to +4. Okay, we had to lose electrons to go from -4 to +4. That's why we became positive. We lost electrons, which was oxidation. What happened to the number of oxygen bonds? It increased, also oxidation.
Why do you have two of the same ones up there?
I don't. That was appropriate, wasn't it? Simple typo. Copy and paste. Bites you every time. So let's take a quick moment here. Just see. So with the answers over the top, what do you have questions on?
2.
Number 2. Why is 2 neither? Okay. Remember your reduction and oxidation rules that we put up on that previous slide, looking at the number of hydrogens and oxygens, is a rule of thumb that gets us through most examples. This one becomes a bit questionable. Okay. The broader definition has to do with how the electrons are being shared around that individual atom, which looks at homolytic versus heterolytic cleavage, which means any atom that is more electronegative than carbon will take electrons away from it. So if we switch chlorine for oxygen, is anything changing to the carbon? Ultimately, both atoms will take the electrons away. The oxidation state for carbon stays identical. So we can tweak our definition. Instead of saying, looking at oxygen, we can look at more electronegative elements. Covers the bases. Any other ones you had questions on? What? 3. I did them fast, so maybe I did something wrong. If we take a look at 3, what changed in the process of 3? So one thing that's suspicious on that is you almost always have an implied hydrogen, which may help out. The carbonyl doesn't change. The oxygen bound to the carbon, we lose an oxygen and it was replaced by hydrogen. Okay. One thing that might pop up is, what happened to this hydrogen? Do I care? I don't care about that hydrogen because it's not attached to the carbon. Okay? Not a big deal. The idea is to practice. potentially throw some of the wrenches in there and see what happens. Okay,
Can you repeat?
go ahead.
Can you repeat what you said about number 2 in terms of the more electronegative?
What you can do when looking at the definitions here is instead of saying decrease for reduction, decrease in oxygen bonds, change oxygen to more electronegative. And more electronegative than what? Than carbon. Why are we looking at carbon? Because it's organic chemistry. What if we switch to a different field where we weren't looking at carbon? More electronegative than whatever that atom is, and it would still apply. Okay. For our oxidation reactions, we can increase in more electronegative bonds than carbon, or more electronegative than carbon bonds. Kind of makes sense? Okay. So, within our oxidation reactions, okay, so the other part of this that pops up is that we end up with this Cyclopenta Intermediate, if you will. So in the course of all of these reactions, we end up with an intermediate where the alkene makes up 2 atoms of a 5-membered ring, and then our reagent makes up the other 3. Right? We've got 2 common reagents showing up in both of these. We've got a metal oxide, and we have ozone. Right? The metal oxide tends to supply a heck of a lot more, or 2 more atoms than we need. That's because those 2 atoms, just aren't part of the 5-membered ring. So what happens is we look at our alkene reacting, Okay. All of these things are happening at the same time, very similar to the Diels-Alder reaction, okay? Except we're missing an extra atom from the Diels-Alder. Okay. If we switch to ozone, what happens in the case of the ozone? Well, the electrons go out to our oxygen. We get, for all intents and purposes, the exact same mechanism, whether we're using the metal oxide or we're using ozone. Do other things happen after this? Yes, absolutely, and it usually turns into a big mess, okay? Which is going to be one of the things I want you to keep in mind when looking at these reactions. We will talk about the mechanisms and go into and start to evaluate them, but we are really only evaluating them because we know what the answer is. What you are ultimately responsible for all of these reagents, the answer. Okay? If you see OSO4 and an alkene, you give me a Syn diol, or sorry, a cis diol. Okay? If you have an alkene and permanganate that is cold, you give me a cis diol. Okay? You are ultimately only responsible for knowing what the answer is out of all of these. Okay? And I know some people don't like that, particularly in a class where we're pushing mechanism and understanding how and why. The mechanistic details in most reduction and oxidation reactions go through a big mess that we don't really want to open up and look at too far. And you'll notice the textbook is taking the same approach I am. We'll look at bits and pieces of the mechanism, but not the entire thing, because the entire thing snowballs into this giant mess. Okay?
So on that first one, the metal,
Mm-hmm.
so you said you got that, so that become a lone pair on the metal hanging out?
Yep.
And then the oxygen on the top right, that just becomes that lone pair, I guess?
That top right?
Yeah.
Nothing happens. Not part of the mechanism.
So does that become a double bond, or is it just still single bonded there?
So what I'm trying to show in the case of the metal with those dotted lines is it's sort of resonance. There is some overlap between the metal and the oxygen, and depending on what metal, you get a stronger overlap or a weaker overlap. So you kind of threshold between the single bond and the double bond. Okay. So what you're primarily concerned about is your alkene comes out, reacts with an oxygen, which causes a pi bond to break. It's not a single bond. The pi bond dumps electrons onto the metal. Why would that even happen? Why would oxygen accept more electrons? It's a weird question.
I know because I listened to your lecture.
Oh, I didn't realize I gave an answer. What did I say in the lecture?
It's because the metal is surrounded by 4 extremely electronegative
Good.
atoms, and so it's going to take the electrons from that lower right oxygen to satiate, I think.
Yes.
Is that correct to use?
Oh,
Other
really? Oh, I picked fun words.
oxygens, yes.
What we are looking at is, if you can't understand one arrow, shift to a different arrow. See if another arrow makes sense. That initial arrow of our oxygen accepting electrons, now shown in blue, may not make a lot of sense. But change your focus to the metal. What does that metal have around it right now? A lot of very electronegative elements, a lot of very electronegative oxygen sucking electron density away. That metal starts to get irritated enough that it can steal electrons from one of the oxygens. That now pisses off the oxygen. The oxygen needs to get electrons from somewhere. That's where our alkene comes in and helps out. Okay? Would oxygen ever just give up its electrons willingly to the metal? No. That's why this has to happen all at the exact same instant. Okay? Once that metal has picked up extra electrons, it's now got too many electrons around it, and that facilitates the breaking of that last oxygen metal pi bond, and it conveniently is now located immediately next to an empty p orbital from the alkene, and it can dump the electrons in. Okay? Exact same thing is happening with our ozone. Why would our oxygen accept more electrons? Well, it can. Why would this oxygen take electrons? It's positively charged. It wants electrons, so it starts to steal them from that oxygen anyway. Okay? As long as the alkene is close enough in proximity to facilitate this, we get the immediate transfer of electrons around. That empty p orbital now happens to be perfectly aligned with the negative charge. The negative charge can very quickly and easily shuttle those electrons in, forming the last leg of our cyclic pentane ring-ish ring. Okay? Questions on that? It's kind of a neat reaction. So, Diels-Alder, all at the same instant. Our metal oxides, all at the same instant. In the case of the Diels-Alder, we have 6 atoms as centers, which means we end up with a cyclohexane type structure. With our metal oxides, we only have 5 atoms involved in the mechanistic step, which means we end up with a cyclopentane type structure. Similarly to the Diels-Alder reaction, though we don't see it quite as cleanly on the Diels-Alder, all of those bonds need to be forming on the same side of our pi bond. Okay? In the case of our metal oxide center, we can show that by showing wedges or dashes, as long as we stay consistent. So in the case of the osmium tetroxide drawn here, I drew one as a wedge, which means the other one must be a wedge as well. Okay? Why do we not get wedge and dash? Structurally speaking, how do you connect, say, the top of my hand and the bottom of my hand to one thing out here? Okay? It's how do I get my elbow and my thumb to connect to the same thing? Okay? Structurally, that's not easy to do. If we add enough carbon atoms in there, or enough atoms into that ring, we could potentially link it, which could be some fun chemistry to play around with. But structurally, it's not the easiest thing to do. So we're going to expect them to both show up on the same side. Okay. The issue with this structure is we now have a metal involved in our organic compound. Okay. Metals are toxic, bad, so we always try to eliminate them in some form or another. So what will end up happening is we add some other reagent to help facilitate and kick out the rest of it. Anybody have any questions about predicting the answer to that following reaction? If you have any questions, you might just look at the drawing right above it. It's the same structure. Yeah, oh, that was kind of dumb. So let's change that one. Let's predict the product of this. And that slid on me, so give me a second. Whoa. What product do you get here with the osmium tetroxide? Okay, you'll notice that a second reagent is being added. That second reagent is to remove the osmium tetroxide and leave behind the alcohols, or leave behind those oxygens, if you will. What's that?
It's just going to be the same as the first one, right? Or not?
Did I provide this exact one on the last one? No, I didn't. No, I didn't. So what product do we get? Focus on the skeleton first, then worry about stereochemistry. Maybe stereochemistry is irrelevant. Give me another 10 seconds. Come up with an answer. Draw faster. The other thing I could say to that is you already have the slides. All you got to do is draw the answer. There's our skeleton product with our OHs, now at both points of the carbon. Is there stereochemistry involved in this? Yes, so we need to specify it. How do we specify it? We need wedges and dashes, so how should we do that? There you go. That's where we're starting. I'm saying the OH is wedged, which means the other OH is wedged. And that means we will necessarily have to make that methyl dashed. What if you don't dash the methyl?
Then you have to dash the OHs.
What if you just didn't dash it? You just left it as a solid line. On the online homework, you would absolutely get it wrong. You might lose some small amount of points in a short answer, okay, on an exam, because I'm grading it by hand. I'm more lenient. Okay? Is this the only answer?
No,
Remember, your alkenes have two sides of your p orbitals. You have a top and a bottom, which means we also have the product like said, or like so. Officially, you'd have to draw both. Again, some of that comes down to the way the question is asked. They just say provide a product, all you need is one. You provide two, you'll get marked wrong because it asks for only one. If it says provide products in parentheses with that S, careful. That ends up falling in kind of this weird gray area. You should probably supply both and then see what happens. Okay, questions? Okay.
So those are the end products then? We kind of skipped the part where like the osmium.
Exactly right. We'd skipped all that middle part. All you're responsible for as far as mechanism goes on that would be in that very first drawing. Okay. The oxygens coordinate to your alkene, the osmium picks up electrons, and you form that cyclopentane-ish intermediate. That's it. You'll notice that the textbook, and this is straight out of the textbook, what do they show in the next sequence? A bunch of arrows where they're saying some stuff is happening, and they aren't showing any of it. Why not? It's messy. Right? And they don't want to get into it. So anything that's like that, you're ultimately not responsible for. Okay? I know, this is one of those dissatisfying things. You're like, I want to know how it works. Sorry. If you don't want to know how it works, just memorize it. You're okay. There's another way you could go through and do this. Same process. Except we have this conditionals thing. Okay? We have to have these conditionals mentioned. You won't just see permanganate floating out on top. You'll see cold and dilute. So in this case, we have the cyclopentene, potassium permanganate, hydroxide, and cold. The dilute may or may not be implied, so you got to watch out for that one. The cold cannot be implied. Okay? So you'll see that specified either by them saying cold or, what's that? Hopefully they don't do that to you by just saying no heat or just not including a temperature. What was that one? 0 degrees Celsius. Okay? Or even a negative Celsius value, meaning cold. Okay? You get the exact same result out of this. You end up with that same cyclopentane type intermediate. That can end up getting cleaved off, and you get the Syn diol, or the Syn addition with the cis diol product. So,
Does it not do anything? It won't react if it's not cold, or does it do something different?
it does something different if it's not cold.
What does it do?
We'll talk about that. Okay? So you again are responsible for that first step to your cyclopentane type intermediate. Okay? After that, you're just responsible for knowing what the product is. What do you think the product is of this one? I'm going to end up drawing the product to the left. I'll give you voting there. How many of you came up with this for an answer?
7 wedges.
So number one, do you need wedges and dashes? No, because we don't have an sp3 atom. Those are all sp2 carbons. There's no need to specify wedges and dashes. Okay. So not a bad first start, but what functional group is that? It's an enol. What ends up actually coming out of this? Turns out as your diketone. Okay. So watch out for that triple bond messing with your alcohol additions. Questions?
So the intermediate that we're responsible for showing would be just
You are responsible for this guy.
that's it.
I left off the double bond. That's it. Okay. With giving you such a simple mechanistic step, what are the odds I actually ask a test question on provided the mechanism for this?
Say likely.
Only one mechanistic step, and you think I'd ask you for the mechanism? Yeah. Maybe if I was trying to help you out a little bit, that is possible. Okay. Not super likely. So, which brings us to this next issue. We're going to take a slight pause here, and we're going to look at something known as oxidative cleavage of both alkenes and alkynes. If we take that alkene and we oxidized it, we put on the two alcohols. But if we push that even further, we can completely cleave the alkene open. So what we're doing is adding this extra step. We do the oxidation, ta-da, diol. And then we go super kaya, and we break it open. And we've now done an oxidative and cleavage reaction. Okay? There are a couple reagents that will go through and do this. Permanganate. What did we just talk about? Permanganate as a diol formation. What's the subtle difference that you might notice already? It says concentrated as opposed to dilute. You'll almost always see concentrated actually specified, and almost always written as CONC, okay, the abbreviation. Other ones that can potentially do it, periodate ion, which is solely mentioned in the textbook. I'm not going to talk about it. And the last one, ozone. Those are our three primary reagents that will all go through and do a complete oxidative cleavage and split these into the corresponding carbonyl compounds. Okay? Come on, screen, work for me. So, permanganate. Strong oxidizing agent. Okay? It's very hard to stop at the dihydroxylation. Really, the only way we can stop it is by keeping the reaction very, very cold. Okay? And minimizing the amount of permanganate present. Those are the only two ways we can stop it, is just don't put it in, effectively, and keep it super cold so it can't move. Okay? What happens if we now switch this up? Notice the change in the conditions. We've got the conch showing up, and you see 50 degrees Celsius. It's not cold, it's not really hot, but it's definitely not cold. Okay? That is our hot qualifier. Okay? You probably wouldn't burn yourself. Yeah. So what are these conditions going to perpetuate? What's the first thing that happens when you put permanganate with the alkene? Hint, it's the part you're responsible for knowing. We end up forming that cyclo intermediate. As far as the rest of the reagents go, okay, if that's actually present, we would fully expect that to also be cleaved off to leave us with the diol. Okay? So at low concentrations, I'm going to remove the stereochemistry on this, we would expect the diol to form. We're at high concentrations. Okay? What is that going to mean as far as the species that we might expect in this first step? And as a hint, it's easier than you may think.
You just get a permanganate pair attached?
You keep the permanganate attached. It doesn't cleave off. Okay? The only reason it can come off is because there's nothing else to help change that structure. Okay? So if we put in a lot of permanganate, now it can't get cleaved off as easily. It's now stuck on there. Okay? So that's our first condition. The concentrated permanganate keeps that on. Next condition that changed was hot. Where have we seen hot or heat before? So we could think to kinetic versus thermodynamic reactions. We've got 5 classes of reactions. Elimination reactions. Guess what that heat is helping to facilitate? An elimination reaction. Okay? So how could that possibly work? We need to somehow break that permanganate off. Okay? So permanganate will take some electrons. We're facilitating the breaking of that bond. But now what happens? Permanganate has, or the manganate has, too many electrons. So what do we have to do? Give some electrons back. Where do we have electrons that it can ditch? We could go to the double bond, but that doesn't facilitate the rest of our reaction. Those electrons can come back down. What happens to that carbon now? Too many bonds, or ultimately too many electrons. What's the issue with the oxygen on the other end? Doesn't have enough electrons. What happens? Draw that result. You follow those arrows around, the result is that you kick out the manganate, and you're now left with no longer a 5-membered ring, but now a chain. This tends to be a favorite question on, not personally of mine, and I'll explain why in a second, but on the ACS. Because you will never see this as an answer. What will you see instead? what they will show you is the now as linearized version as possible. We formed the product, and then they spun it all around. So now, hey, look, it looks neat. That's why we did it, not to hide the fact that that reaction just did a ring opening. Okay? So remember, your structures can spin, flip, and rotate as long as nothing prevents them from doing so. There's another issue with this. Are these carbons fully oxidized? As a hint, when we looked at our reduction and oxidation reactions, when we said oxidation, what was our definition for oxidation? Adding oxygen bonds and decreasing hydrogens. Are there any hydrogens on these carbons? Yep. Are these fully oxidized? Nope. Very beginning, very hard to stop oxidizing, so don't stop. Okay. Permanganate will continue to oxidize as long as it can. So under this circumstance, guess what happens? Okay. It will continue to oxidize. How it oxidizes becomes the next question. So let's evaluate that and pause for a moment. What's the reactivity of our new functional group? What reactivity do you see in this structure? What functional group do you have? You have a carbonyl or an aldehyde. What reactivity do you see within that structure? I'll give you another 5 seconds to think about it. Okay, double bond, what do you see with the double bond as reactivity? We could evaluate the electrons in the double bond as being reactive. They aren't all that reactive because it's not the same as an alkene. Why is this different from an alkene? We have the oxygen. Why does the oxygen mess with this? It's really electronegative. Okay, so we do have that alkene, but that pi bond, but those electrons are pretty well tied to the oxygen. There's no hydrogen in that bond. If the electrons are tied to the oxygen, what happened to the carbon? It's partially positive. Can we do anything with a partial positive? Say with any of the reagents that happen to be floating. Whoa, wow, I just broke my pen. With any of the reagents that happen to be floating around, like a negatively charged hydroxide. What happens? That goes, oh wow, I really broke my pen. Okay, we'll just switch to fingers. Nope, oh, it's an eraser, that's why. Okay. The result in our sidebar is that we can take any carbonyl and react it with ultimately any oxygen nucleophile, say like hydroxide or water or an alcohol. And we can, instead of having that be two bonds to the same oxygen, we can now have still two bonds to oxygen, but those oxygens are now different oxygens. Okay? So as long as we're under this heat reaction and we have the hydroxide as a nucleophile, we can actually react the hydroxide with this, and we end up with this system. Okay. Let's ignore the protonation states for the moment. What is special about this product? What functional groups do you see? Alcohol. And carbonyl, but I'm going to ignore that, so I'm going to cross that out. And still something not circled. Alcohol. How many alcohols? What's that known as? Diol. How did this whole reaction start and move? When the diol reacted with permanganate. What do we have? A diol, which will react with permanganate. Okay. The permanganate facilitates the second oxidative step, we work the reaction up with H+, and we'd end up with our final answer. What will that final answer look like? What's this next oxidative step? We started here. A single oxidation takes us to a carbonyl. What happens as another oxidative step? We need to have what? Another oxygen. Add the hydrogen. We've got the carboxylic acid. So the result is that we end up with a carboxylic acid. Okay?
And it would do that to the other side. Right?
Predict the answers. The first one. What's the deal with the first one? Where did that starting material come from? That look familiar at all? That's the exact same problem we were just working. And we said that it did not stop at the aldehyde, that it went all the way to the acid on that one side. What about the other side? Exact same thing happens. You have to end up with the diacid. Second reaction. What do I need to add? What's the biggest thing missing right now in what I've got drawn? The methyl. I'm missing that carbon. That carbon was attached to the alkene, and that alkene became a carbonyl. So one of those, I'd better have a methyl hanging off of it. Now what happens? Permanganate, we oxidize the crap out of it. What happens? We need the OH, not an alcohol. Fix that for me. Carboxylic acid. So here's a carboxylic acid off one end. What do we do to the other? What?
Nothing.
Why nothing? Why do I not convert that other carbon into a carboxylic acid?
Because it has the methyl group, so it has one.
Yes, something to do with the methyl group. What happens in our oxidation reaction? We increase oxygen and we decrease hydrogen. Is there any more hydrogen attached to that carbon? No. Can we oxidize it any further? No, because there's no hydrogen to remove from that carbon. I can't oxidize it any further. The alkene or the permanganate will stall at a ketone. It can't oxidize further. And what we could kind of pretend to do off of our previous slide, let's erase this. If we adjust and now put this in as a hydrogen, how can we get the oxidation reaction? Well, we still have strong base present. This can come in, pull the hydrogen. The electrons can shift to form the carbonyl. Electrons go to that manganate. These electrons come back to the oxygen. It has nowhere else to dump its electrons. What's the result? Double bond and why do we add the acid? To put the hydrogen on that last oxygen so that we've got our permanganate. Why, when we switch to that, whoa, sorry, I just realized that was the wrong button. Instead of it being a hydrogen, it's a methyl. Why does this reaction not happen? Why does the carbon change things? That first arrow, now our red carbon had to take electrons. Where is it getting those electrons from? It's getting it from the atom that's attached. What's the difference in electronegativity between carbon and carbon? None. Would those electrons be polarized? No. What happens if I change, stupid eraser, change that atom to now being the hydrogen? Yeah, now it can take those electrons. That bond is polarized enough that we can initiate that. Okay? It's the subtle difference between hydrogen and carbon that's facilitating either that elimination, which gets us to the acid, or it stalls at the diol, which, if we look at our examples on the far right, technically favors our carbonyl, not the alcohol form. Okay? Kind of a neat little process going on with that. How much of that mechanism are you concerned about? The very first step. Everything else is oxidize it out. So let's look at some shortcuts on this. I'm going to redraw it, except I'm going to stretch that double bond to be really massive. That's 4 carbons. Let's try that again. Now we got 5 carbons. Now what am I going to do? Erase the stretched part and put in oxygen, oxygen. Now evaluate what is attached on that carbon. Are those hydrogens or are those carbons? Hydrogens, which means add another oxygen. There's my answer. Yeah, easy as that, right? Erase, oxygen, oxygen. I got a carbon out there, so I can't put in an oxygen. I have a hydrogen out here. There's my oxygen. There's the answer. It's kind of bizarre how stupid that is, isn't it? What if we switch to this? Wherever I have an alkene, what happens? Erase it. Oxygen, oxygen. What's out there? Hydrogen, so it needs OH. What's out this end? Careful. Hydrogen, hydrogen. What do I do? 2 oxygens, also known as CO2. Okay. What happens to the rest of that ring? There's a lot of pi bonds in there, aren't there? Oof. Nothing. Stays aromatic. The ring structure is incredibly stable. We do not treat those with permanganate. They don't react. How about in the next one? Okay, this is where it gets weird. Can I have a triple bond to oxygen? So how do I fix that? Just add another oxygen. What happened to the ring? Is that an aromatic ring?
No.
Nope, which means I have to oxidize them. Because I have hydrogens out the yin-yang on this thing. How many answers do you fill in? Sorry, I kind of lost that carbon out there. You get 3 structures as an answer. I have seen this question show up at least in the study guide. Okay. I don't remember if it actually shows up on the final or not. Okay. So the triple bond ultimately does the same thing, except now instead of there being a hydrogen or a carbon, there's nothing. Okay, accept electrons. We need to put in an oxygen. You have to satisfy that bond. Okay? So what I was trying to do on this last part was give you the shortcut. Gets you to the answer. Because that's ultimately all you need. Questions?
Can you go over why CO2 is formed? I understand why the first, you cleave the first one and that's the O in the end, but what about the O?
So when you cleave that last one, it would come off as this guy, right? Okay. Those hydrogens would oxidize, and you'd put on another oxygen. Which is more stable, having two oxygens or one oxygen with two bonds? It's easier, if you will, to have one oxygen with two bonds than it is to have two oxygens with one bond.
Would they ever show the other, the initial one as an answer?
No, they should not. And that's an oxygen at the end. Okay. Look at you. I think there's a couple more slides. We are officially done here, but we'll just address those real quickly. All we end up doing is using ozone now to go through and do the same process. Same exact idea. Ozone's a little bit easier to work with because with the permanganate, you can't stop. You oxidize the crap out of it and that's done. Okay, so we can't get an aldehyde when we use permanganate. Ozone, on the other hand, will stop at an aldehyde if you supply the proper reagents. Okay? So ozone gives you a little bit more control over where you stop. You'll notice the last product they've got shown here gives you that aldehyde as your functional group. Okay? Sorry, I'm done.